Get started here. It's about that time. So I'm going to introduce myself. My name is Todd MacDermid. This is Eric Brandwine. We both work for UUNet, and let me discuss a little bit of the background of the problem. We work for UUNet's a medium to large sized ISP, and we have lots of hosts out in the field. And we were starting to notice occasionally kernel mod rootkits popping up on a few of them. And this is problematic for reasons that we'll go into, but we decided that we had to work on this problem and get something figured out. So first we're going to go into what kernel mod rootkits are and how they work a little bit, and then we're going to go into what we did about it.
So we've got some background information here, but we'd like to go through it quickly. We're aiming for Jeff's 20% alienation mark, and we'd like to get to the meat of this. Just a couple bullets on what a kernel module is and does. The two important things to note here are, one, the kernel module is the operating system. It becomes part of the OS. There are no permissions barriers, no authorization barriers. It's running in the memory space of the kernel. The other important thing is that kernel modules get loaded real time without any hiccup whatsoever in system services. That means there could possibly be absolutely no notification whatsoever to a systems administrator, even if they're watching.
I'm just going to also point out that we have a default permit on any questions, so unless we explicitly deny you, please feel free to speak up anytime. So, problem with security is no one runs authorization on the kernel. The kernel is what runs authorization on userland processes, but if the kernel says to do something, the hardware does it. I mean, that's as low as you get. The first publicly available reference that we saw to rootkit kernel mods was in FRAC 55. 50-5. And I'm sure they were out there before then, but they weren't as widely known. And detection of them is pretty impossible with standard userland tools. You basically either have to hope that the rootkit author made a mistake somewhere or didn't cover something. And it doesn't help if you loaded in trusted binaries off CD, because the system calls themselves are lying to you. And so just replacing your PS binary is not going to help. Evil kernel mods will lie about their existence. So, as black hat tools move into the kernel, white hat tools have to go there too in order to have any hope of detecting these things. There are a few tools that do exist that attempt to deal with the kernel mod problem. KStat does some cool stuff, but unfortunately it runs in userland largely, and it can be fooled, and we'll show how you can do that. Carbonite is a good one, loads into the kernel and takes a snapshot. Lionfind basically capitalizes on mistakes that the kernel mod authors made. But by and large, there are not a lot of kernel mod rootkit detection tools out there.
So if you're programming in the kernel, as you are with kernel modules, you're working in kernel mode. User mode is the good old Unix we know and love. You've got memory mapping, virtual memory. You can't waste the system because the kernel protects you from it. Everything is nice. In kernel mode, it's a lot like working on a much older system. You can have direct access to the hardware. You can bypass the memory mapping hardware. You can change memory maps. You can directly touch things and completely waste the system. The primary entry point for kernel mode is system calls. That's how userland processes request services from the system. And that makes them an excellent choke point for monitoring the kernel and kernel user interaction. Under Linux, the strace tool, Solaris, its truss, just prints out system calls as they're made, arguments, return values, interprets them as best it can. And it's a wonderful tool even if you're not working in the kernel, but for us it was invaluable. It is worth it to note that system calls are not the only entry point into the kernel. Signals, hardware interrupts, other things, but system calls are the primary way that user processes enter the kernel.
So we're going to talk about how kernel mod rootkits work, and actually how Fnord works largely as well. When a syscall is made, basically the address of that, the number associated with that system call is loaded into a register on Intel hardware, and an interrupt is made. And basically the kernel will go and it will look up that number in a table, the syscall table, and it will jump to the memory location in that table, and it will execute that function, which is usually, in a healthy kernel, the open system call, sys_open. These entries can be replaced, though. It's not actually checking the location of the symbol, what the symbol maps to. It's going to what's in the table. And if you replace that with some module code of your own, hacked_open, hypothetically, you can jump to that location. Hacked open can modify return values. It can modify arguments. And then, well, it'll usually call the original open call at some point, so you don't have to re-implement the entire open system call yourself. But it'll basically screw with what's going through. And the userland process has no way of knowing what's really happening here. All it says is, oh, great kernel, I wish to open this file. Please give me an FD back. And you'll get it or you won't, and it'll return an error code, and you don't know what happened behind the scenes, how many functions it had to jump through to get there.
So this is a diagram of what system call wrapping in the stack looks like. The dotted yellow line is the user space, kernel space barrier. And in reality, the two stacks aren't actually joined like that, but conceptually, this is how it works. The user makes a system call. The kernel jumps into that system call. You can see the arguments passed from the user to the system call. Some work is done by the system call, and a return value is passed back to the user. If the system call is a blocking system call, the process goes to sleep, and the system call is still left on the stack. Lower left diagram is what it looks like when a single module has been loaded that wraps that system call. The kernel has no idea it's there. The system call has no idea it's there. The user has no idea it's there. The user makes the system call. The kernel jumps to the address that the module is specified in the table. The module has a chance to alter the arguments and then generally calls the system call. The system call does whatever processing it would normally do, but then it returns back to the module. The module then has a crack at the return value before returning to user space. Of course, not all modules have to wrap system calls. Not all system call wrappers have to call the original system call. But here with Fnord, we're interested in obfuscation, not in actually doing work. So we leave all the actual work to the kernel, the original. One other thing to note about this diagram is if a process makes a blocking system call, it goes to sleep in the system call. If the module later gets unloaded, when the system call tries to return to the module, the invalid memory address, or worse, something else has been loaded in that space, you jump to an arbitrary memory location. Generally, the process wastes itself. If you're not lucky, the machine wastes itself. And you may see that here because we haven't fixed that. The proper way to handle it is to increment the module use count every time you block within one of your system calls, and then refuse to unload the module if it's in use. Just for ease of demoing, we have commented that out, so any processes exploding are likely caused by that. The right diagram shows what happens when a second module has been loaded and wraps the same system call. They're called in LIFO order. In this case, Module 1 has no idea of Module 2's existence. Module 2 isn't necessarily aware that when it calls down to Module 1, it isn't calling into the actual kernel. And you can see that each module gets a crack at the arguments on the way down and the return values on the way up.
So, what's out there right now? What is published and publicly available? Adore is a fairly popular kernel mod and one that we're going to abuse in our presentation. Version of it that we looked at hides files based off of owner UID. There's a special owner UID, and if you try and open a file with that UID in there, it fails and says there's no such file. Kmod was presented last year by Job DeHaas at this very conference. Excellent presentation. It's a Solaris-based kernel mod. We started off with a Solaris-based kernel mod ourselves. We had issues with 64-bit kernels. His kernel mod that we got also does as well. We think we've got the problem figured out, but we were spending so much time having fun with Linux that we couldn't go back and check it. If you want to get into Linux kernel mods, there's a paper on Packetstorm that's a tutorial on Linux loadable kernel mods, and there's a ton of different loadable kernel mods included in that paper that do a lot of different things. And that's a good place to look if you want to learn about that kind of stuff.
So we've got this thing called Fnord. What are we trying to do with it? It provides something akin to tripwire for the kernel. We are not trying to guarantee that your kernel is doing what you think it's doing. Working within the constraints that we have and the framework that Linux or Solaris presents to you, if it's not impossible, it's a very, very difficult problem. And we've got a large team of cranky systems administrators, and if we start messing with our systems and making them work in new and interesting ways, they're going to come down on us. So the machine still has to look like it did. It just has to work a little bit different. So we attempt to guarantee notification of a kernel integrity breach, not prevent the kernel integrity breach. We're here, we're presenting. It's obvious that this thing exists and that we're working on it. And when this does get rolled out on our network, all of server ops is going to be aware of it, all of network security is going to be aware of it. We have to assume that people that are attacking our machines are aware of it as well. Kernel module-based rootkits tend to hide below the low water line. As long as the administrator doesn't look for them, they don't raise their heads above water, and the attacker is happy. People are attacking a unit, they're doing so for a reason. They know that Fnord is there, they're going to be actively looking for it. So we have to hide Fnord itself very well, not just from people that could trip over it, but from people that are actively looking for it. So that means that wherever possible, we've avoided security through obscurity. We've patched all of the holes that we could find. Next.
Most of the holes that we could find.
There's always another hole.
Yes.
While we were in there implementing all of the stealth for Fnord, it was very easy to extend that to providing stealth for other traditional userland tools, as well as other kernel tools. So we have flexible, configurable stealth for others. In addition, Fnord can be administrated live. And to prevent anyone poking around in the system from noticing you doing this, the administration of Fnord can be hidden as well. While we were in there messing around with the kernel, we provide a lot of silent alarms and logging. Fnord has a separate logging channel that's not based on system logging. And of course, it's hidden by Fnord. If attackers can't see it, they can't disable it, they don't even know that we've caught them. And in addition, for our uses as a general system integrity checker, this would be ideal for a honeypot. As we'll go into later, a full root compromise of the box does not mean a full compromise of the box. There's still things that a root user can't do.
So, what were our objectives? I mean, how did we differ from kmod rootkits that are out there today? We wanted to deploy this on every box, or as many as we could. So it's got to be, everything's got to be scalable. We've got to log in a scalable fashion. We've got to be administrable in a scalable fashion. And we've got to have no operational impact, which means that if the choice comes down to security or it works, the box has to work. I'm sorry, but the routers can't go down, and they've got to stay up. And we'd rather have a functional, broken into network, which is a horrible, horrible thing to say. We wanted to separate security administration from systems administration. A lot of people have root. We have a lot of systems administrators, and we don't want them to have full control over the box. We wanted there to be something back, something further that we could basically use and check to make sure that the box was still being healthy and that no one was abusing their root privileges. We wanted it to be able to be administrated while still in stealth mode. A lot of the early kmod rootkits, you had to take them out of stealth mode, change your configuration files, whatever, and then turn them back on. We wanted to avoid that. And we also didn't want to have special tools available on the system to administer it. So we didn't want to have to depend on non-standard ioctls or things like that, where you'd have to have the compiled binary in there to actually talk to the module.
So this is a list of features that Fnord provides us. And I'm going to go into each of them in much greater detail. This is just a preview of things to come. Todd, next slide. So you have to deal with Fnord. You have to be able to ask it what it's doing right now. You have to be able to reconfigure it. And all of this while it's live, while it's installed on the box, actively hiding things, actively doing its job. And to provide this, we have a pseudo character special device that Fnord can register on the VFS, and this allows for interaction with users. It's a lot like dialing a remote system. You type in human readable commands, you get back human readable output. It's very simple to work with, and my favorite Fnord administration command is cat. It's guaranteed to be there. In using this interface, you can specify files, processes, network connections, modules, device drivers, etc. to hide or show, configure the logging, and also query the module as to what it's currently doing. So the character special device is nice. It provides a lot of flexibility, a lot of convenience, but there's a limited number of character major numbers, 256 in our case. It would be very easy if the module had the interface registered all the time to detect this. Even if you removed it from proc devices, you can look in proc devices. Anything that's registered is clean. Load a module that loops across all the other car major numbers. If you can register on any of them, they're clean too. If you can't register on anything, clearly something is wrong. Fnord is there. So we dynamically register and unregister the interface based on userland actions. We'll explain LEET in a couple slides, but if a LEET process makes a character special node, and the name of the node matches the secdev string, and that's just a pound define in our module that we're demoing, it happens to be spipe. If it creates a car special node with the name spipe, and that make node succeeds, it registers on the major number that that node was created with. The minor number is ignored. If a LEET process removes that node, the module automatically unregisters the interface. It sounds a bit confusing, but the bottom line is if you make a node to talk to Fnord, Fnord will be there. When you remove the node, Fnord is no longer there. So Fnord's not there, but I make myself lead. Fnord is there. And I picked 42 because I happen to know it's not registered at the moment, and it's a good number. If I could type, it would have worked. Okay, so you can see on 42, spipe is registered. This is a non-LEET ordinary root shell. And you can see on 42, there's no entry. So
now the non-lead root shell could still detect it at this moment by registering attempting to register all device numbers right now, which is why it isn't always there. We only put it there when you're administering it.
okay, so for example, so currently the module is hiding the Fnord module. If you wanted to hide other modules, type in a command here. We've got a file log. Now the module's hiding log. If you type ls, it's there. In the ordinary shell, it's gone. Let's clean up after ourselves. And it's back. And then if we have to make it not in use, remove the node, and it's gone.
We are going to go into the details of exactly how this is done in a few moments. We're just demonstrating
the interface and showing what it can do. And so at the moment, there's no trace within the device tree or the file system that Fnord exists, even though it was there a moment ago. So this is great for users, this is great for configuring the module, this is great for security administration, but we have thousands of deployed hosts that we have to watch continuously, and touching each machine on a continual basis is not possible. It doesn't scale. So we have to be able to gather information from the module without touching it. So we provide a logging channel parallel to the standard kernel log. And this logging channel is very similar to the standard kernel log. We provide sprintk rather than printk to the kernel. Unfortunately, if you export it beyond the module for use by other modules, it's visible in the symbol table, so we don't export it. And then we provide proc sk message rather than proc k message to user space. And of course, this whole thing is hidden by Fnord. So if we, you can see here, these are the output messages. It's got a 16K ring buffer, and I hadn't read from it yet, so these are all of the things that have been logged since I've been in there. And you can see if I recreate it, module logs that it registered it. If we remove it, it unregisters it. And using this, it's possible to obtain status from the module without actually being on the box.
Normally, there would be a modified Oh, is it? No, it isn't.
Oh,
Normally, there'd be a modified syslogd on listening to proc sk message. Oh, I'm sorry, it is.
it is. I told
Go
you.
for it.
The intention of this, if you look, the beginning of every line is tagged with a number in brackets. That's the log level. This is identical to proc kmessage in operation, and the idea would be that you'd hack klogd and syslogd so that klogd read from proc sk message logged to a non-standard syslogd, and the syslogd would read a hidden config file and log to a security-related log server. We haven't written that yet, but we did get the module working. And any changes to the module configuration are logged out this for audit purposes. So if someone does hijack the module, at least we still have something.
So we've shown you a little bit about leet processes. You've noticed that one of these processes is not like the other. The bottom process can basically see everything, and the top process can see nothing. And that's because one of them has an environment variable that the other one does not. That's called delete var. And if you actually do an env on the bottom one, you'll see that we've got leet var equals the leet string, which is basically a password. And we store the MD5 hash of that in the module. And so every time we make a system call where information could be hidden and we've got to decide whether or not to show it, we check to see if that environment variable exists on that process. And if it exists, we hash the string that it's equal to. And if the hash matches the hash that we've got stored in the module, we let it see it. So all the hidden files are visible to the leet process. We don't modify any file contents for the leet process. You notice that proc modules was modified. And only leet processes can cause registration or deregistration of the admin interface. We hashed it so that you can't recover it from it. Now, you've noticed that we've got this sitting in clear text in the environment variable, and that would be a problem. So we do take care of that.
So here it is in the leet shell, and you can see it's present in the environment. 528 is the process for the bash running in the lower window. If you do it here, I guarantee you it's not there. Null terminated records are good for computers, but not for humans. But we can have grep tell us that it indeed is missing. And you can see that the module is watching us, and it knows when we open up environment files. So we want to hide things. We want to hide things like tripwire. We want to hide things, our scripts. We want to hide our specialized syslogd. So we want to hide files by and large. We hide them based off of dev inode as opposed to strings. We do that to avoid string collisions. A lot of kmod rootkits use a special magic string, and if the file contains that magic string, then it is hidden. This causes a problem of you generally put all your special files into a special little directory, and we didn't want to get locked down to that directory. We wanted to be able to hide files anywhere on the system. We wanted to be able to hide files with any name, and we didn't want there to be any chance of collisions. We didn't want an admin to accidentally create a file with the same name as our hidden string and then go, wait a second, why am I not seeing the file I just created there? So what we do is origstat is called on each file access attempt, which is the original stat call, and it derives the dev inode pair from there, and from that determines whether or not there's a linked list that stores all the currently hidden files, and it stores their dev inode pairs. And so it compares the dev inode pairs. If it matches, that file's supposed to be hidden, and if the process is not leet, it shouldn't see it. We do have a problem with raw disk access. You could open up the raw disk device and read from there and determine the entire contents of the file system that way. A lot of the files that we hide in proc, and there is no corresponding raw disk device, and we do log attempts to open raw disk devices. We went with the BSD secure levels methodology. You know, if you open dev kmem, that's bad. If you open raw disk devices, that's bad. But we don't stop it because we don't want people to know that we're there. We want people to think that everything is okay and hunky-dory, but we log the fact that, oh, look, someone's looking, maybe they saw us by now. So that gets rid of actually touching files, but you can also list directories. So we also wrapped get directory entries. We we have to stat the derpy that's passed into getDents to get a device type. But once we've got that, getDents gives us inodes for free. And then we just alter the return value. We call the system getDents, and then alter the return value, taking out all of the entries we don't want to be there. And then all syscalls that take char star path were wrapped to return no entry if the file is supposed to be hidden. This includes things like swap on and, things that you would never think of. But we wanted there to be no little edge that you could peel back. Actually, at one point I'd forgotten to wrap unlink. So you could try unlinking files, and if the unlink succeeded, you knew there was something there, but you'd never get it. It was already gone. That's since been fixed. Another problem that we've got is, for example, link and a couple of other syscalls take char star path, char star destination, and what do you do for the char star destination? No entry is a nonsensical return value for the destination. Of course there's no entry, you're trying to create it. The only advice we have is don't try and hide things with really obvious names. The only way to work around that is to catch the overwrite, dynamically off-name it within the kernel, update all of your config files, update everything else, and it's more code and more trouble than we were willing to go into. Because things are hidden based on device inode, it's very easy to hide things in hide processes. Under Linux, it's easy to calculate the inode number for proc PID given PID. Left shift at 16, add 3. Process 509 is the tail-f varlog messages in the lower left window. So we can repeat that. It's still there. However, it's gone. It's no longer visible to the non-leet shell. You can note that proc sk message noted that every single environment file on the disk on the system was opened. It's because it was a ps-efa. I was querying every single process for all of its information. It's also logged at level 6, and you could throw level 6 to the bit bucket and just pay attention to the important messages. And 1, 2, 3, 4. There it is.
Should also point out, last year, Job DeHaas mentioned that one of the problems that you had with file hiding, if you really wanted to do it right, was if you catted the directory, it's in there. We do file content alteration, so we could catch that, but under Linux we don't have to, because if you try and read from a directory in Linux, it returns an error. So, yay. So, I just said that we alter file contents. How do we basically have several lists of files that we might want to mess with. We'll get into those lists in a moment, but we've got several lists that we all want to mess with in certain ways. And so if those files are opened, it checks every time a file is opened to see if it's on one of these special lists. And if it is on one of these special lists, we store the process ID and the FD of what that file is. And so every time we read that from that process and that PID, we can go around and mess with it. We also wrap close so that it removes them from the lists, and we wrap lseek so that when you lseek to that, it gives you an appropriate offset within the newly altered file. That's not an easy problem, and it does get a little bit processor intensive. Another problem that we have is fork and dupe will change the PID FD pair. Fork will change the PID, obviously, and fork is a real bear to wrap, so we haven't done that yet. And dupe will change the FD, and we just haven't gotten around to wrapping that yet.
So that's all the bookkeeping involved, but the actual work of altering the contents of a file is done in read. For each file descriptor that we're interested in, we have a data structure that includes a 4K buffer. We chose 4K because it happens to make the data structure a little bit less than a page, which is real convenient in the kernel. But the first time read is called, this buffer is filled, the modification function is called on it, and this can shorten, lengthen, or alter the contents of the buffer, possibly 2 of the above. And then the user request is satisfied from this buffer. If the user request is smaller than the valid data left in the buffer, we save the buffer for the next time they read. If it's not enough to satisfy the user request, we repeat the whole thing over and over again, and we use a sliding buffer window that I'll go into in a second to catch all interesting records, even when they fall on buffer boundaries. The current lseek implementation, whenever you seek, starts at the beginning of the file, reads sequentially through the entire file, doing this over and over and over again until it gets to an effective offset that you've specified. This is not horrendous for short files, but for large, long files, the whole purpose in using lseek is to jump over the beginning, and we've just negated that. It's really a tough, difficult problem, and probably shouldn't be implemented at the system call level. It probably belongs in the file system, if anywhere. It's just unpleasant. So this is a diagram of how the sliding read buffer works. On the initial call to read, a buffer is read in, 4,000 bytes. The modification function is called, and there are different lists of file descriptors to be modified, and there are different modification functions, and we'll go into that. And in this case, a short chunk has been lopped off the end of the buffer. The buffer has gotten shorter, a record has been removed. The user request, the blue chunk, is satisfied from that buffer, and there's still some amount of valid data left in the buffer, so that's stored in our module until the next time. Eventually, the buffer is going to be down to 1,000 bytes of valid information. We shift that information to the beginning of the buffer, refill the buffer off of disk, that's the green chunk there, recall the modification function, once again another record is lopped off, and then repeat the whole cycle, starting to return data back to the user. 4,000 and 1,000 are arbitrary numbers. In our case, 1,000 bytes was guaranteed to catch all of the interesting records that we cared about, and 4K, as I said, happened to fit page size. Those could be tuned as necessary. Yep.
So, what files exactly do we alter? What is in our default file modification list? We modify proc modules so that if you read from proc modules, you will miss seeing our module. We modify procnet UDP and procnet TCP so that connections to given hosts on the remote end will not be seen if you open those. We modify proc devices so that you don't see our special device. And we modify proc PID environ so that if you're not leet, you can't see the leet string. You can't see the existence of the leet string, much less what the value of the password is. We also modify dev kmem. We modify it slightly differently because instead of removing records from there, we're replacing values. We do that so that kstat can't see the changes that we've made to the system call table. And we also note that someone opened dev kmem in that case. We tried to hide the system call table differently. We found some interesting bugs about that, but we'll go into that in a second. Yes, question?
A couple slides back, you mentioned that handling one byte is a problem or multiple or something. What was the special case that involved there?
The problem was that if we were just looking for records, the original implementation, we were looking for a special record, like the leet string equals whatever. And so we were matching to see if we had something leet string equals whatever in our buffer, we'd remove that from our buffer. Well, if you read 1 byte at a time, if we're just looking at the user buffer, then we're going to look at L. Well, that not necessarily is part of leet string, so we wouldn't do anything with it. E, whatever, and they would get it back 1 bit at a time, and so you could get an unmodified file by just reading it 1 byte at a time. So we implemented the internal buffer so that we could look at the whole thing, figure out if it was part of what we wanted to remove, and then just return back what you wanted.
And we have caught modules in the wild that failed to catch that.
Yes, another question. Every time you lseek, we throw out the entire buffer that we've got and we read it all in from the start. So that's an interesting timing attack. You'll be able, I mean, it's going to take a lot longer than a normal lseek would, but it will still return our modified file. You won't be able to get around it that way.
We don't handle negative offsets, that is offsets from the end of the file well. Really, in order to do that, you'd have to run the modification function across the entire file, figure out what the modified length of the file is, and then start working backwards. And because things slide off the left side of the buffer and disappear, if you're if you're more than 4K from the end of the file, you'd have to go back and start from the beginning and seek all the way up to where you want it to be. It's really unpleasant. There's not a lot you can do about it.
All right. Do you want a demo file alteration, or?
I just did.
Oh, okay.
So if we look in proc modules, I just did this, but I'll speak through it. This is a pretty stripped-down Linux box. There are no modules loaded by default, so that's proper output. But in the leech shell, Fnord is loaded, taking up about 60K of kernel space. And the use count is currently 1 because I'm reading from its device. Also, if you look, spipe is registered on car major 42, and it's not there for the non-leech shell. Doesn't exist. Of course, if the non-leech shell loaded a module that attempted to register or something on car major 42, they'd get a very weird error message back, and that would be the start of us being uncovered.
Which is why we don't leave it registered all the time. Another thing that we did with is we messed around with query module a good chunk. If you query module for the list of modules in the system, you won't get back our module unless you're elite. And originally, the way that we fooled kstat was that we kept a separate system call table in memory that was our good system call table, so that whenever you asked for, because kstat gets the location of the syscall table by through the query module system call, and so we'd return a false location for that system call, or for the syscall table. And that fooled kstat, but unfortunately, it fooled other modules as well, because apparently insmod gets the location of the syscall table that way as well. And so if you loaded a module on top of our module, it would look like it was loaded, because if you looked at the system call table, it was there, but it never actually got called, because the system call table that it had loaded itself into was not the system call table that system calls were getting called from. So that broke. So now what we do is we return the real location of the system call table, but when you read from dev kmem, we'll return false locations for what's in the system call table. And that's good.
Okay. Do you want to do the
Okay,
query
I'll
module thing?
Do I want to do it with what?
Query module for lsmod? Or
No. So basically, what we can do is, has everyone used kstat? Anyone use kstat? No one has ever used kstat. Okay. Basically, it's a cool tool by sikoreza.org, which basically goes through and it will compare the system call table entries with the sys_open, for example, locations. So it'll actually look at the location of the system call, and if the location of the system call does not match what's in the system call table, it prints out a little warning that something's not right on your system.
Okay, I just unloaded Fnord, and you can see the rmod process seg faulted just like I said it would. It's because we wrapped the system call that's used to remove modules and didn't bother to fix that. That can be fixed, we just haven't. Anyway.
Oops, and you lost the shell too.
Yeah.
Okay.
Anything that executes a blocking system call while the module is loaded has problems.
Issues. So now what we're going to do is we're going to show you what kstat looks like normally. And that's a healthy kstat. There is one system call that does not match. It has not matched on any Linux box that I've ever been on. So either Red Hat has some serious issues, or it's just that way by default. We haven't gone into the source to figure out why that is. But if we load another kernel module, say adore, for example, and then run kstat and grep for warn, you'll see that the system calls that adore wraps, kstat picks it up. And that's a good way to detect loadable kernel modules on your system. But it can be fooled because it's coming from userland. And since it's coming from userland, we can lie to it, essentially, when it asks to read dev kmem. So we remove the door, we load Fnord in, and we run kstat. This is from the leech shell, so it's not going to lie. And you can see we have a lot of warnings, because that's everything that we've wrapped right there. But if we run it from the non-leech shell, it looks normal. It looks totally natural. Now, if you load adore on top of our kernel module and then run kstat, we do update the table as it's supposed to look, so that you will actually see that the system call tables get modified. And our module will log also the fact that that got loaded. We'll get into that in a couple slides. Any questions to this point? Okay. So another little feature that we have is we have append-only files. And append-only files are on the special file list, and open is also wrapped such that if you open it read, nothing happens. That's normal and natural. If you open it write only or read write without the append and you're not lead, it will trigger an alarm via SK message and will save off an unaltered version of the log file and will hide it. And then it will proceed normally, and you can play with the file to your leisure. So if we had a hypothetical log file that is first, second, third, fourth, you know, really boring log file there. If you want to append to it, wait, that's not append. If you want to append to it, nothing will happen because log files are supposed to be appended to. Okay? But, and
Oops.
yeah, you overwrote it.
Yes, I did.
Okay.
What is the append command?
Is echo, it's append
Append
file, yeah. So
Okay.
now this file is protected. And if you append to it, nothing will happen to it, except the write will happen in a normal way. And if you cat it, it'll look normal on both sides. But if you try and modify it, delete that incriminating third line, it'll look like it worked. And it's still there, and everything is fine. But we've logged the fact that you've changed it. And we've also saved off an unmodified copy, which is going to be log.3 in this particular case. And that's automatically added to the hidden files list. There's some interesting things that we have to work around with log rotation with this, which we haven't totally figured out yet, but we feel that this is a pretty cool capability that we're going to be able to use somehow. Yes?
This sounds great for hiding things while an attacker is still in user mode.
Mm-hmm.
Trying to come in.
Yeah.
What happens then when the attacker attacks
Mm-hmm.
and gets kernel mode modules put in?
We will notice them.
Yeah, you notice them and log them,
Uh-huh.
but then after that, he's in the kernel.
Yes. And if we're going to let him
Can he circumvent after that?
pretty much anything he wants. He is the kernel at that point, and if he's aware of our existence, he could go on a little seek and destroy mission and find all our sections of code and parse what we're doing and hunt us down and kill us, and we are toast. And he could
Absolutely.
notice the hidden files, and he can do anything he wants. If you let someone execute kernel mode code on your machine, you're screwed. And that's a decision that you've got to make if you're going for stealth. Are you going to let him do things? Or are you going to forbid him from doing things and alert him to the fact that you are forbidding him from doing that? The real solution would be a virtual machine. And that's a lot of money that we don't have. We would really like a SP2 to run thousands of Linux boxes on. But
So we would catch the breach of kernel integrity, hopefully. We would notice that he was doing things on our systems. We would be alerted. He may be able to, hide some of his traces, but this is completely hidden. I mean, there's no trace of it. You can't see that the log file is still there. You can't see that your records haven't been deleted. Your SSH connection attempts are still in a file somewhere on the file system that we can analyze later. And remember, but he has to find out that they're there to be changed in the first place.
he needs to know that the open call has been wrapped. So he would have to know that Fnord has been loaded onto the machine to know what to change in the kernel to allow him to see those files. He could do anything that he wants once he's in the kernel if he's aware of what the kernel really looks like at that point, yes. And the kernel itself, I mean, if he wanted to take this to the logical extreme, he could go through as the kernel and, poke at every byte and see what's in every byte and analyze exactly what's happening in that machine and determine that we've been loaded that way because we cannot hide kernel data structures from the kernel.
It's a memory dereference. It's not a function call anymore. There's no hook to wrap. Remember our constraint. We've got a large deployed network of Solaris machines. Unfortunately, this isn't Solaris. And we've got to keep them working exactly the way they work today with no operational impact. If we screw something up, server ops is going to come down on us like a load of bricks, and we just can't afford that.
Right. So we know that he's there. We can send the ambulances running, and hopefully he won't be able to disassemble our kernel in the time it takes us to get there. So, but by and large, we're catching 95% of the people out there, I'm pretty sure, with this.
Are you hiding the fact that the files, the files are still there for the
No, that's
Oh,
very
sorry.
difficult.
Well,
I-
do you?
I guess if you wanted to,
You would hide it.
If you wanted to, you could do some accounting and figure out that, your hidden files of saved off log copies are, so many blocks, and, alter the accounting that DF would return. DU is more difficult. Actually, no, we would fix DU because they're
Right.
hidden. It wouldn't stat them. It wouldn't be in the directory entry. DU
Right.
is taken care of. DF would require some bookkeeping. It doesn't matter when your partition fills, and no amount of bookkeeping is going to make more space.
That's true. DF would catch that.
Hopefully your logs are not the majority of your disk and the change is relatively minor. Most of our deployed systems have enough churn in their disk that, a couple kbyte log file coming or going is below the noise level.
Yes.
On your hidden files, I don't think you like iron star or iron directory.
Star gets expanded by the shell. The shell does a get deents on dot. Get deents says that file isn't there. It's still there. Now, if they rm star cd dot dot and try and remove the directory, it's going to tell you the directory isn't empty because the reference count of the directory inode is going to be too high. There's not a lot you can do about that either. However, someone that attempts to remove var log, it's going to cause all sorts of things to scream.
We could actually, instead of saving the file in the current directory where it is, we could copy it to a different directory and save our unaltered copy there. But we don't implement that right now. But that's something we could do. Yeah. No-
Some other...
If we ran fdisk and
No,
fix the
because
reference count?
fdisk would be ideally running as lead. I hadn't thought of that, and I haven't tried it. But I was intending to sacrifice this laptop after the conference, so maybe later today I will.
Yes.
Doesn't work. Doesn't work. You're still going to rely on some system call, open or stat or something, and it's going to fail. Size of kernel memory.
It's a linked list. We just keep adding to it. You'll notice longer and longer times. Right.
You're still talking milliseconds at extreme cases. Because this logs, every time a log file is opened for editing, it'll log, and that should never happen. And hopefully, before months have passed and the disk is filled up, one of us would take a look at the machine. This is for, frontline defense, notification and preserving forensics evidence, not for long-term guaranteed.
Okay.
And that final bullet there is important. Someone logs into one of our machines, ext2fs can do append-only files. Well, that's ext2fs only. It doesn't work on Solaris UFS, and it says no. I'm like, uh-oh, something's wrong. I can't get rid of my log messages, and they clear off the machine. Here, they edit the log file. Attackers are likely not going to be on console. They're across some internet link from some country far away. They don't have exact timing information. They edit the log file. They remove their connection attempts, whatever else they want to do. They hit save. It saves. They're none the wiser. They don't know that anything has happened. They believe that they've successfully covered their traces, and we still have all of the log entries.
Can you talk a little bit about node monitoring for your hidden log reporting?
Up here, we provide /proc/sk message. It's parallel to proc kmessage. Our module logs out of that. There's an sprintk function that the module has access to. Writes logs into a ring buffer, and you can just read from it. The goal is to hack klogd and syslogd so that it reads from there and reads a private hidden syslog.conf file and then logs to a security log server. Obviously, at the far end, you're going to have Swatch or something watching and, parsing out the noise and looking for the interesting messages. Some things have some noise in them, but system calls being wrapped, log files being edited, things like that should never, ever, ever happen on a deployed Unix system. And any occurrence of them is almost guaranteed to be a positive. False positive rate is very low.
Cool.
So what we can do with this, we can hide traditional security tools. If you want to run tripwire on the box, Fnord watches the kernel for you. Fnord is not a user space security tool. Tripwire is, though, and you could run it. You could run it on the box. It runs as lead. It has access to the entire disk, including its config files, its log files, its database. But an attacker comes onto the box and they start poking around. There's absolutely no evidence that tripwire is installed on the system. Likewise with a host-based firewall or a host-based IDS, and similarly with honeypot monitoring scripts. You're watching your system binaries, you're watching what's happening. Doesn't matter. If you get root on the box, you still can't delete the log files. You still can't delete traces that you were there. We've put barriers on root. It's not a large box that we've secured, but it's there.
So the real reason where we started with all this was kernel integrity. We wanted to monitor the syscall table and basically make sure that no one had loaded kernel modules on us. And so the meat and potatoes of why we did this is we wanted to look at this. Now, kernel data structures can't be modified for an in-kernel viewer, and we can compare syscall table entries to exported kernel symbols, and that will catch already installed kmod rootkits. That can be extended to other data structures, processes, and some such. We think the system call table gives us the biggest bang for the buck. That's the structure that everybody seems to want to go after, and so that's the one that we monitor right now. But we would like to extend it to other future ones. So we check syscall table and make sure that all is good. We wrap all the system calls that we can. And whenever install module or delete module is run, after it comes back, we check to see the system call table entries right then and compare them with exported kernel symbols. In addition, if someone manages to load a kernel module not via install module or delete module, we have a timer that's checking every second, and all discrepancies will alarm. We had some problems wrapping the following system calls for fairly hairy reasons, but we do check every entry in the syscall table, all 256, not just the 191 that are in use. So,
and it would be really, really hard to write a rootkit with just those 3 system calls, so we're not horrendously worried.
But we check them anyway.
So we've got Fnord loaded. It returns the expected information. The non-leet shell is clean. The leet shell has Fnord. If we insmod a door, you can see it has logged the fact that all of the system calls that a door wraps are indeed wrapped. And working with the system has to work the way it used to work, this is also visible in user space. If you rerun kstat in the leet shell, you get fairly garbage output because you've got the union of the adore and the Fnord system calls wrapped.
If you bother to check the addresses, they will match up with new addresses. But we've logged the fact that a change has occurred out to the remote system call, syslog server.
And the name of the module. One other thing that we keep meaning to implement but haven't is saving a copy of all modules that get loaded in some hidden directory, so that later on when we have to investigate them, the fact that they removed the module from the file system after they loaded it is no longer a problem.
It's more of a honeypot ideal.
Oops, wrong window. So we remove a door, and you can see it's logged the fact that all of those system calls have been unwrapped now.
That's what we did. Now, things that we could do against this. How could we get around Fnord? Because we've been thinking of ideas of, okay, our module is interesting, but it's not bulletproof. Things you could do that would really screw with us is you could rename the exported symbol exported symbols before the initial checks are run. So you load in hacked open, and then you actually change the symbol name so that hacked open is actually sys_open. So when we check to see if what we're pointing to in the syscall table is sys_open, yeah, we are, and you rename sys_open to something else. That would really mess with us. So we haven't seen any of that yet. Maybe now that we're out there, we will. Good. If you wanted to, you could unwrap the system calls before each time that we check them and then rewrap them after we check them. That would basically require you knowing when we're checking them. So you could check the timer. You could install a kernel module in such a way so that after it installed itself, because we check immediately upon return of the install module call, it goes through and sets itself so that, you know, a millisecond after it returns, it rewraps all the system calls and then unwraps, rewraps every time the timer's called. That would be kind of a hairy module to write. There are probably easier ways to attack us.
And it's not SMP compliant.
No, it would not be SMP compliant. You could spoof the location of the syscall table like we did the first time that we tried, such that when we were looking at the system call table, what we're looking at is not where the system calls are actually going to get their addresses. So that's basically changing one value in the kernel and not changing the other. So it's still kind of an arms race. If you get into the kernel before we do, there are ways that you could prevent yourself from being detected by us. And as long as we're allowing attackers to execute kernel mode code, you're going to have that kind of. These are pretty involved attacks. They're not trivial. They're not out there now. But it is one of the disadvantages of having a soft permissive module. The advantage is obviously you get great intelligence and they don't know you're there necessarily.
And your systems administrators don't kill you.
And your systems administrators do not kill you.
And bear in mind that our constraint was a large network of deployed systems. The idea was that Fnord would be added to the build. So before these machines ever touched the network, before there was ever a chance of compromise, barring corrupt employees and all that other happy stuff, Fnord would already be there watching. So we would be the first. We would have the advantage. It's our box, and we would guarantee that we were already installed before there was a chance. So just to...
Yes?
What happens if you try to install Fnord and it's already there?
It will detect itself. It will detect the fact that Fnord just got loaded on top of me. And
Someone else had.
Yeah, Fnord qualifies as a kernel mod rootkit as far as Fnord is concerned.
it will log itself, the fact that it got logged on top of itself. Yes?
Well, how big do you consider the chance that if you can write malicious payment and so get one block entry, print your module down and hit it, and then so you only have one entry in your log file payment will link to and that's it.
Yeah, we should follow up. I mean, writing to dev kmem is a big deal, and that should be a big alarm that goes off huge.
That is the case for Linux payment. I don't think it will go for Solaris.
Really? Things write to dev kmem directly in Solaris?
There are several groups, at least for indexes, I'm not sure why.
Okay. Well, if it's not a regular tool, we could try and pass by fiat. Please do not run these tools on our systems because we'll come down hard on your ass. That's really annoying. If you allow users to write into dev kmem, you're kind of bending over for them.
Now,
But
what,
how big is the chance to, I mean,
it,
to run down your module once everyone knows how it works?
well, everyone knows some of how it works, but you don't have details, you don't have a hex dump, you don't have a copy of the module itself, certainly not the source code. We don't think that any of these ideas are truly revolutionary. This is the evolution of the kernel module. This is the next step in the chain, but I'm sure that someone out there has thought of these things. And we would rather that the security community be thinking with us than one day I log onto a box and it explodes in my face. If someone had excellent or perfect knowledge of our module, they could get in there, they could alter kmem, they could disable our module, but we would get that one critical log message out. The vast majority of attackers, we would have excellent information on them, but hopefully all of them, we would at least have some sign. There would be some notification. I hate to say it, but it happens, and I've seen it happen at our company, and I've seen it happen other places. Boxes get owned, no one is watching them, no one is monitoring them. I mean, I've been alerted to compromises. Someone called me because their lab network segment was saturated. Turns out that it was a Ware site, and everyone and their brother was downloading MP3s off it. That is not how you should find out that your system is compromised. There were actually traces on one box that hackers had been pushing each other off the box. Someone broke it, patched the hole they came in through. Someone else came in through another hole. It's like, no, it's my box. That shouldn't be happening on our systems. And it's not just ours, it's everyone's. So we're trying to guarantee that as soon as they gain access, we're notified, can shift services to standby boxes, take this one out of service, and start trying to figure out how they got in, and guarantee that they don't do any further damage.
I would not recommend that you install classified material or anything like that on a box that's running Fnord. I mean, that is a totally inappropriate application of it because it is soft, but it's a step above Honeypot. I mean, it's a really kick-ass Honeypot, and it's something that can be deployed widely so that all your systems become Honeypots to a certain extent. Mm-hmm. No, that's an excellent thing to start doing.
We could MD5 selected areas of memory or something similar.
That's a really good idea. We'll start doing
However, right, and there's also that paper on loading modules into non-modular kernels, and that really scared us. The bottom line is they all require something that trips one of our alarms. If you're going to alter the kernel, either you have access to the box before we do, which violates our constraints, or you've written to dev kmem, which violates our logging. So, once again, we don't try and fix everything. We just try and let someone know that something's awry.
Yes?
How do you fix the 64-bit Solaris kernel thing with Java?
Well, I don't know this because we haven't tested it yet, but supposedly there are two different system call tables in Solaris, one for 32-bit and one for 64-bit. And I think our basic problem was we were writing to the wrong system call table. I might be totally wrong because I really didn't spend any time on it at all because we were working on the Linux version, but I'm thinking that. Okay.
Right, but those are provided for user processes to select which one they wish to call. There are not, there's open and open 64, but there's not a corresponding 64 version for every single system call. And the kernel does provide 32 and 64-bit versions for both of them, as well as a 32-bit shared linker and a 64-bit linker, libc, libm, everything has to be duplicated. And it's a nest of worms. We spent a fair amount of time reading kernel source, and that's a lot easier to do in Linux than it is in Solaris. So that's why the Linux version is here today.
Are we done with the slide?
Not quite.
Not quite.
One possible application of Fnord is incident response, forensics. You throw it at a machine in an unknown state, and it could do basically what kstat does, but from within the kernel, so you avoid the system call layer. Obviously, if you mess around within the kernel enough, you can lie to even kernel modules, as we have started to do. But it does catch the great majority of existing kernel modules, in fact, all of them that we're aware of. And it's probably about an hour's worth of coding based on what we've got so far, but it isn't quite implemented yet. It does a fairly good job of protecting the system from future kernel module-based rootkits. And if you get to the system in the beginning, the future is all of time. There is no window of vulnerability. Hides itself virtually without a trace. We think we've plugged all the holes in the file system layer and most of the standard OS services. Certainly made it much more difficult than most.
So, where would we, oh, I'm sorry, wrong slide.
We mess with most of the kernel tables already, and we'd like to extend it more, so you can hide device registrations, processes, network connections, files, ideally anything that the kernel keeps state on, hide and show them dynamically, as well as query it as to what's currently hidden. We provide logging that attackers are not aware of and cannot detect from on the box, ideally. And this lulls them into a false sense of security and gives us added notification. We protect our log files silently, and that ties in with the bullet above. And can be administrated absolutely without special tools. You don't need to, for example, Adore compiles Ava, and you need that executable of Ava to administrate that version of Adore. And it changes with each compile. You don't need to compile something that uses weird ioctals. You don't need to include anything. Standard system binaries will allow you to do anything that this module can do.
So now, where would we like to go with this in the future? Couple things we'd like to add. We should add the system call MD5ing to verify the integrity of the system calls themselves. We would like to mangle the stack in such a way so that TCP dump itself could not see the outgoing traffic that it's sending to the syslog, the secure syslog server. We would like to add or create a loose source routing kernel module so that it basically, the box for given IP addresses will insert itself as the midpoint of a loose source route conversation. That really has very little to do with the kernel integrity, but it's a really cool idea that we would like our bosses to okay us to work on. So we would like to verify more kernel structures, and we'd like to port it to Solaris. That's nice.
I love Windows. Also, with the loose source routing, for honeypotting, if you loose source route all traffic validly, you enable loose source routing on your honeypot box and some other box in your network, you can effectively set up a sniffer. You loose source route everything through some other box on your network, hopefully not on the same segment, and that way you have a crack at all traffic before the source route is incremented to the next hop. And hopefully the remote host would honor the loose source route. Obviously there are some problems with that, and it's a lot easier to plug in a sniffer, but it's a neat idea. That's nice.
Hello. All right.
Apparently charging your battery fully is a bad idea.
Excellent.
So we're here, we've got this kernel module, and that means we've done a fair amount of kernel programming. And the bottom line is kernel mode programming sucks. You have no debugger, you get to read all sorts of esoteric hexadecimal stack traces. It's really horrendous, and if you do decide to get into kernel mode programming, the best piece of advice I can give you is get a machine that reboots an F6 quickly. It happens all the time. Sometimes the box explodes violently. The screen goes black, and you see the BIOS messages. You don't even get a chance to read what's on the screen. It's just gone. But we figured we'd share some of the stumbling blocks we ran into while we were going through this. Kernel mode is quite limited to provide the maximum amount of possible memory to user mode processes. So the kernel stack is fairly short. And we actually overflowed it. We allocated several large automatic variables on the stack, and in this case large is page size, 4K. And it was at 3 or 4 pages on the stack, we crashed it into the heap, and the box rebooted spectacularly. It was amazingly painful to debug because each of the functions worked perfectly individually, but if you happened to call them in the wrong order, boom, the box disappeared. That took quite a while.
Good rule of thumb is automatic variables are bad, malloc what you can.
kmalloc or
kmalloc.
Get free page and
Right.
read all about it. We do a lot of accounting based on process ID. Process IDs get recycled through the life of the system, and it'd be a shame for me to hide a Fnord administrative process, and then weeks later some user starts up a shell, and the shell can't see itself because it happens to have used the same process ID. So we wrapped _exit, which is how processes commit suicide. Unfortunately, it is possible for a process to exit without going through _exit. In the Linux kernel, there's a function do _exit, which actually does the work of tearing down a process and returning its resources to the system. And in particular, signals circumvent _exit, and processes get killed by signals all the time. Do _exit is not exported. We didn't want to re-implement it, and it can't be overwritten because it's not in the symbol table. Possibilities are either to watch fork and see when process IDs are recycled. That's the lazy version. You wait until you have to replace them. Or you could watch wait PID and wait for a parent to reap status on a child and check to see if the status of the PID of the child matches one of your interesting processes.
Another interesting issue that we had early on in development was rewrapping system calls and overwriting our exported symbols because we were exporting our symbols at that point. So we would load Fnord or wrapmod, it was at that point, and then we load wrapmod on top of that, and it would have an orig_open syscall entry, basically. It was a symbol. And so the first one would wrap and orig_open would be the value of orig_open, and the second one would load, and orig_open would be the value of the first module, hacked_open. And so the second module would call the first module, which would call itself again and again and again until we ran out of kernel stack and the box died. So generally, you probably shouldn't be exporting symbols anyway if you want to be stealthy, but that was something that we hit early.
I'm about to unload Fnord, but I'd just like to point out, if you look in the varlog messages, other than the processes that exploded because they were doing blocking syscalls, there was absolutely no trace of Fnord in varlog messages. And I believe I'm logging star.star at the moment. But either way, there are no system logging indications that Fnord exists. Of course. And rmmod blows up again. So we've got a clean box. So the way system calls get called, you put the system call number that you want in a register, you call interrupt 80. It turns out that strace triggers off interrupt 80. So interrupt 80 gets called, strace looks at what's on the stack, and prints out a line for the user. This normally works quite well. However, if you make system calls from within the kernel, a lot of the documents tell you that you should use the _syscall wrapper. So you type _syscall2 to generate a system call that takes 2 arguments, and you pass it all to goo, and it returns something that you can call that will call this syscall. It actually generates the assembly language glue code that you need to call interrupt 80 with the register set up correctly. This triggers interrupt 80 again and generates an extra strace line. The best way to do this, if you want to keep stealth up, is just get the address of the system call you're interested from, ideally from the syscall table, before it's modified, and just call that directly as a function pointer. That will work, it'll work fine, and there won't be any oddness. So if we insmod syscallwrap.o, so we're just going to cat log, and worked fine. Syscallwrap.o is stupid. It just wraps open and stats everything that's passed to it.
But it stats it via the syscall wrapper, and so it's actually calling int 80 from within the kernel.
And you can see it's logging itself in syslog, and it's telling you, dev inode pairs for everything that it opens. However, if we look at the trace file, every time open is called, you get this spurious eno_sys function.implemented line. And that happens every time a system call is made using int 80 from within a system call that's executing on behalf of a user process. You get it every time. It is consistent. You can see it happens on the ld.so.cache, which succeeded. And if you scroll down long enough, you can see when we open the log file we're interested in, it happens again. There's nothing wrong here. There's nothing bad happening. But if you're going for stealth, this is bad. This is a dead giveaway that something is wrong. So don't do it. You can take this one.
Okay. Reading into kernel buffers is a classic problem, but it bit us anyway. Basically, when you try and read into a kernel buffer, the read system call itself believes that you're still executing on behalf of the user process, and so it will interpret the pointer that you give it to the buffer as a userland pointer unless you change your memory map. And so it'll write it to some random part in user, probably corrupting the user process and not giving you what you wanted in your kernel land buffer. So make sure that you change your memory map so that you're actually pointing at kernel space before you call the read system call to try to read into a kernel buffer.
And it's probably almost unreadable, but in the lower right window there are the 2 macros that we used to accomplish this. You basically save off the old data segment, the value of the data segment register.
Scroll it up a little. Just hit return a few times. Get it higher.
And then set the new one for kernel space, and then when you end your kmem, so just wrap anything that you want to operate in kernel space with begin kmem and end kmem. Works beautifully, simply, makes sense.
We would be remiss if we did not mention that this is not a perfect approach to kernel integrity. It's the best one we could think of given the constraints that we had, but there are other people that are out there that have been working on the same problem. BSD secure levels is a good way. It prohibits writes to dev-kmem, prohibits reading raw disk devices after the secure level hits 1. You can't load new modules. There are a lot of modules that after they get loaded, any new modules that get loaded in after it have to be cryptographically signed. Linux secure module interface is currently under development. It's going to be a set of hooks that go into the Linux kernel, which you can load arbitrary mods in. And one of those things that those mods could do is they could do cryptographic signature checking. They could disallow any new modules. So it's not really an approach in and of itself as it is a set of hooks for you putting in what kind of approach you want. And it's a pretty interesting development. But most of them are hard solutions. They forbid tampering with the kernel. Thou shalt not. And so you instantly know that they are installed. You know that you can't tamper with the kernel at all. So a soft approach, while it opens you up, gives you stealth. I mean, it gives you flexibility, and it gives you capability to develop intelligence that you wouldn't have gotten otherwise. That's all we've got.
So O'Reilly has given us this nice T-shirt that we're supposed to give to someone. So bring on the questions. Cricket chirping.
Yes. Unfortunately, our bosses are, this module, while it is excellent, can easily be turned into a rootkit. And our superiors are somewhat worried about the legal liability of potentially releasing rootkitable code upon the world. So while we are more than happy to talk with you about approaches, and if you get stuck on bugs, helping you with that, we can't actually give you code. But we can help you implement all kinds of interesting things. The module itself is not available.
And the module itself still has a couple of rough edges, and I wouldn't recommend it for anyone.
There may be some organizational things that we can work out that we'll have to go through our legal department, and yeah. What do we recommend for what?
There's a couple of references in the presentation, and hire a couple of good security programmers.
Yep. Way in the back. Every time we open a file, or yeah, we are.
Every time we look at a car. No, not a file descriptor. Whenever we look at a car star path, we call stat to get the dev inode. Yeah, you could delve into the you could delve into the file system and circumvent some of it. System calls under Linux are pretty lightweight, and we didn't want to delve too low into the kernel. Calling stat is portable. Just about any Unix system will do it for you. If they change the ext2fs implementation, the function that we rely on has different calling conventions or something, and all of a sudden our module doesn't work anymore. Whereas stat's been there, it's going to be there, it's going to keep being there.
Yes? I'm sorry?
Yeah, we hide the entry in slash.
Kstat minus p. Yes, actually, we have not screwed with that part of dev-kmem yet, so kstat-p would detect it at this point. I'm sorry.
I'm sorry, I couldn't hear you.
Come on down. Uh-huh. Yes, yes, and that would be the next step. The question was, does kstat-p detect hidden processes? The answer is right now, yes, it would. However, we mess with dev-kmem on kstat-s. Could we extend that idea to mess with kstat-p? And the answer is absolutely yes, we could. And that would be an excellent way to do it, and that's probably the way we would implement it. We just didn't
We're
have it.
actively looking into things like that. I mean, we've got the whole framework in place, and now it's easy to duplicate and cookie cutter things and extend that to other kernel data structures.
Still under development. Yes?
That passed my mind. In part, I implemented this because I was lazy. While all UDP packets are eventually emitted by the kernel, it kind of bothers me to have the kernel generating network traffic directly. This relies on standard userland facilities that people are familiar with. I mean, you just have a magic/proc node, and you get log messages on it, and then from there you can do whatever you want with it. If you want to throw it into a hidden file on the local disk because it's your laptop and you travel, you can do that. If you want to point klogd at it and syslog it out to a remote host, that's great. If you have an abhorrence for Solaris syslogd, as some of us do, and you decide that ngsyslog is the way to go, you can point this at ngsyslog and use different syslog clients or something else entirely. One of the things that has been kicked around occasionally is using Radius for authentication and accounting on our machines. And if that ever did come to fruition, we could just point a Radius accounting daemon at this file, and it would log through our AAA system.
Yes? Mm-hmm.
No, that's a dead giveaway. We don't mess with the file system at that level, and for that reason and the LSeq problem and all of that, it's probably better to implement such file mangling in the file system layer. However, all of our files that we currently mess with are in /proc. /proc isn't a file system. It's a reflection of kernel data structures.
Or dev kmon.
And the way /proc works is you register a proc node and you specify, there's an array of function pointers, and you specify when the user opens this, run this function. When the user reads from it, run this function. When the user writes to it, run this function. And the size is reported as 0, so there's no check on it. There's no way you can verify. So it's a problem. It's a hard problem, and luckily it's a problem we didn't have to address.
Yes?
If you release Fnord as source, if someone else compiles it and installs it over your copy, does that give them access since they have enough leak password then?
No, the leet password is, if we ever were to distribute Fnord, we would not distribute a leet password with it. I mean, we have a little function that generates it. And
Right, but if you can install Fnord on top of your Fnord,
uh-huh.
would it then?
No,
No.
You would be leet to your module, I would be leet to my module, and we would have a little war. Right. Actually, you would have collisions because there can only be one proc SK message, so the second module that got loaded would fail to register the proc message. But each module could separately hide different devices, hide different files, and to a user process, the union of the two configurations is what would be visible.
Right.
That would be most unpleasant and a lot of fun.
Yes?
No, in this scenario, the second Fnord qualifies as an ordinary plain Jane kernel mod rootkit as far as the first one is concerned. It would start screaming about system calls being wrapped and addresses changing and people doing bad things. And the systems administrators who are watching the first one, the valid one, would see odd things happening. Anyone else?
Anyone? Well, thank you all for coming.